we will now start to look at methods which are called unsupervised. Consider a data set of webcam snapshots or onboard camera snapshots of a mower robot. Where each snapshot is characterized by two features like the redness, and the greenness of a snapshot. And in one of the exercise rounds, I think in quiz round 3, you were provided with labeled data. So we had a data point with feature vector xi and the label. How did we provide the label? Do you remember? Yes? Yeah, and how did he store the labels? Okay. Yeah, so the label information was stored somewhat indirectly in the file names. So we knew the first 20 images were grass, the next 20 were soil, and so on and so forth. And now assume we somehow messed up the file allocation table, and we don't know the file names anymore, so we don't know, we lost the labels. So we only know the redness and greenness features of each snapshot, and we still want to order them. We want to order the snapshots into two groups. One group which contains images which show grass. It's very important for these mowing robots to find grass. So we want one group which has the snapshots containing grass and another group which shows something else than grass. How many snapshots do we need to label at minimum? For how many snapshots we have to look at them and find out, does it show grass or not? Let's say we have tons of snapshots here, drawing as the scatter plot, and we want to know which one of them show grass and which one of them don't show grass. How many of these data points or the snapshots corresponding to these data points do we need to evaluate, inspect, and find out the label in order to group them into grass images and no grass images? How many labels do we need? How many data points do we need to label? Minimum. 3? 2. I would say you can also along with 1 if you manage to group, if there is some inherent group structure which coincides with the group structure of grass and no grass images, because once you have found out these two groups, you just have to look at one snapshot, for example, this here, and find out, aha, this is grass, because then you immediately know that all of them are grass, and in the other one, there can only be no grass images. So if you manage to perfectly cluster the data set, you need only one labeled data point. And that hints already at the use of clustering methods. They are used often as a pre-processing method that helps you to solve then a follow-up classification problem or a regression problem, a supervised problem. So clustering often used as pre-processing. Can also be interpreted as a compression algorithm, because once you have clustered the data set into clusters, into few clusters, let's say 2 clusters, you can replace all the data points here inside by just a characteristic of the cluster. So what would be a characteristic of this cluster? Let's say this is cluster 1 and this is cluster 2. How could we characterize cluster 1? Yes? Yeah, so the images are very green and very red. So we could try to find the cluster mean, the mean of all data points in this. So let's call this M, which is the mean of all data points, or the mean of all the feature vectors of the data points that belong to this cluster, cluster 1. And then we divide by the size of the cluster, the number of elements in the cluster. So this is called the cluster mean. And then we do the same for cluster 2. So we compute the cluster mean M2. So we can represent the whole data set using two vectors, two cluster means. How can we find the cluster means from the data? Here I kind of cheated a bit because I draw already the cluster structure, but in practice all you get is a bunch of data points which are characterized by features, redness and greenness. So how do we find the cluster means? Let's say we know we want to have two clusters. Sometimes the application or the problem you're looking at, for example here categorizing images into grass or no grass, sometimes this application suggests you what the number of clusters is. So let's say we have two clusters. How do we find the two clusters? If there are two clusters in the data set. Or let's put it another way, how do we find a good choice for two clusters? Sorry? The average distance of the data. The average distance to what? Which, so the suggestion was we can minimize the distance to the average weight. Yeah, from every data point to the current average. So we see already from this formulation there is some circular argument involved here. We would need to find the clusters, we would need to know the cluster means and then simply associate each data point with the cluster which is nearest. On the other hand, we would need the cluster assignment at the first step to compute the cluster means. So what do? We iterate. So we start with a guess, initial guess for the cluster means, M1, M2. M2. So this is an initial guess. Or let's use some color coding here. Initial guess for cluster means. So here, M1, and here, M2. So now we have cluster means. Now we can compute the distance, compare the distance, and correspondingly associate data points with the nearest cluster mean. And it turns out in this case, so if we connect these two and divide in the middle, maybe this could be the decision boundary. So we would say this here belongs to cluster 1, and this here would be cluster 2. So what did we do? We update the cluster assignments. So it is useful to associate for each data point xy, which is characterized by a feature vector xy, a cluster assignment variable yi. And let's say this here yi is 1. So this yi, the cluster assignment gives the index of the cluster. So here, for example, this y would be 2. Okay? Any questions? Pretty straightforward. So what do we do now? We have updated the clusters. Are we happy? Can we now finish? Are we done with clustering. We clustered the data set. So we came up with a clustering method. Is this a good clustering method? Well, it should be somehow, the clustering that we came up with should be somehow be consistent with the means that we have. We have now a new clustering, so what we can do, we can update the means. Update mean, M1 and M2. So this M1 might be then here, for example. M2 might be here. So this update moves the cluster means. So now that we have a new cluster means, what do? We have to update the cluster assignments. So what do we get here? This. So it becomes art. Now we have a new cluster assignment. What do? Update the cluster means, yeah? You know already. This is called k-means. This is the k-means algorithm, by the way, what I do now. So we update cluster mean. Again. So what do we get here? Maybe we end up here with M1. Maybe here M2. So we have new cluster means. What do? Update cluster assignments. So we get this. Oh, what happened now with the cluster assignments? They didn't change. The cluster assignments didn't change. So what do we expect? How much will the cluster means change? Nothing. Stays. So we can continue these iterations if we are bored, but there will not be any change anymore in the cluster means and cluster assignments. We converge to a clustering. And this whole thing here is called k-means. K-means algorithm. In particular, I have demonstrated it for k equal 2. You can also use 3, 4, or 5 clusters. Yes?
But does the result depend on the initial guess?
Yes. So what we found is just one clustering. Is it the optimal clustering? And what does it mean to be an optimal clustering?
So
how do we measure the quality of a clustering? How good is this green final clustering now? No.
Just run the data you can find in clusters. Wouldn't it just move around and never set?
Yeah, the question was, don't we need some cluster structure as an input? Well, no. K-means just needs a bunch of data points, and it tries to find the cluster structure inside the data points, intrinsic to the data points. If there is no cluster structure, it will not yield reasonable clusters. But if there is, under certain conditions, it finds a useful cluster structure. And the cluster structure can be characterized, for example, by looking at the average distance of the nodes within a cluster to the cluster mean. So we can define a cost underlying k-means, which depends on a clustering. So a clustering is characterized by the mean vectors and by the cluster assignments. So for the ith data point, we have a cluster assignment, which is either 1 or 2, depending if the ith data point belongs to cluster 1 or cluster 2. And for each such clustering, so this defines one clustering, a particular clustering. We can define an empirical risk obtained for this data set, this particular data set, which is unlabeled, so we only have feature vectors. So this data set contains only the feature vectors of data points. No labels here. And we can say, well, we just measure the average distance of each feature vector to the cluster mean to which this data point is associated. So this is yi. So what this quantity does, it measures this distance, this, this. Where's the cluster mean? Here, sorry. So it measures the distances within a cluster between the cluster mean and the data points. So this here, this, and this. And it sums them up, and it does the same with the other cluster. Okay? So this is this empirical risk. And the smaller this empirical risk, the more concentrated are the data points in each cluster around the mean. Yes? Good question. I'm not aware of using the squared. Yes, the squared error, yeah. But again, what you use to measure this error is up to you. Depends on the application. You might not use the 2 norm at all, but the 1 norm, or any norm, or distance measure. So there is no optimal choice for measuring the error. It could be also the squared norm. Yeah. Okay. So here we have now a measure that tells us how good a clustering is. And it turns out that this simple procedure here, this alternating procedure called k-means, does the following. It optimizes alternatively this cost or this risk with respect to means with the assignments held fixed. And in the next step, it chooses the assignments to minimize this risk with the means held fixed. So it's a coordinate descent method to minimize this empirical risk. However, it turns out that this empirical risk is a non-convex function. So on the x-axis we have the cluster or the clustering parameters, which is given by the mean vectors and the cluster assignments. And here we have the empirical risk of a clustering, so the error of clustering. And here we have local minima. So what you get out of k-means depends, first of all, it depends on your initial guess. So this red crosses here, it depends on the initial guess. And if you choose it like this here, the initial guess, you might end up here in a local minimum and might miss the global minimum. So this would be the optimal cluster. And this we call a sub or a local minimum, locally optimal clustering. And k-means might get trapped in local optima. That's one big disadvantage of k-means. So how do we cope with the problem of getting stuck in local optima? Well, one easy way is to run this k-means several times, and in each time you choose a different initial cluster mean. So you randomly select cluster means, run k-means, repeat again. Randomly select initial cluster means, run k-means, and again, and then you get different results when you run k-means, and you pick the resulting clustering which has the smallest empirical risk. Okay, so any questions regarding k-means clustering? It seems rather trivial, this clustering algorithm. However, it turns out it's very broadly applicable. And sometimes it's even the best you can do. If you have not any further information, just a bunch of data points without any labels, there's not much else you can do but try to group them into clusters. And if there is no inherent good clustering structure, you might get some artifact clustering, but you cannot do much about it. Okay, k-means is what we call a hard clustering method. Hard clustering means that each data point is assigned to one and exactly one cluster. And sometimes this is a bit too coarse-grained information. If we have a data point which is close to the boundary, for example this one here, as opposed to this one is way closer to the other cluster. It might be useful to know how much or what is the degree of belonging to a certain cluster. Is this data point belonging to a cluster with a high degree of belonging, or is it kind of a border case somewhere here between two clusters? When you want to, for example, for market segmentation, you want to find out to which group a certain customer belongs, then it's good to know if a certain customer is kind of in between two groups. So you cannot really associate it to one group, but you have to take care of two groups to serve him. And this is provided, so the soft information, a degree of belonging is provided by soft clustering methods. So in a soft clustering method, we have again a bunch of data points without labels. And instead of mapping them into non-overlapping clusters, we try to find for each data point a degree of belonging. So if this is the ith data point with feature vector xi, we define a degree of belonging called yic, or let's again consider k equal 2, so the two cluster case. We define yi1 as the degree of xy belonging to cluster 1. But we also define for this same data point another quantity called the degree of xi belonging to C2. So each data point has a bunch of quantities which tell the degree of belonging to different clusters. And both of these values can be non-zero. So this data point can belong to both clusters. So we have one cluster 2 and one cluster 1. And already this drawing should indicate that these clusters can overlap. So there is no clear separation between the two clusters. For each data point, we specify the degrees of belonging to cluster 1 and cluster 2. And for this data point, for example, this data point, which is a border case, we might have, so let's say this would be the first data point in our list. So we have y1. Yeah, it's kind of accustomed to scale these degrees of belonging to the range 0 to 1. 1 means belongs 100% to one cluster. 0 means doesn't belong at all to one cluster. So at this border case, we would have the degrees of belonging being 0.5 for both clusters. So this is a border case. Whereas for this here, let's say this would be the second data point, we would have y21 would be 0.2, y1, y22. So the degree of belonging to the second cluster might be higher. It makes sense to normalize them, these degrees of belonging, such that for each data point, the sum of both degrees of belonging is 1. It can only belong to one of those two, but it can kind of the sum of those two degrees of belonging should not exceed 1. But how now? The question is, how do we find out these degrees of belonging? And to this end, we will do the following. We will represent each cluster by a probability distribution. In particular, we represent cluster 1 by a probability distribution characterized by a mean vector, a cluster mean vector, and a covariance matrix. And we use as a probability distribution a multivariate normal distribution with mean vector and covariance matrix C1. The mean vector has pretty much the same meaning as for k-means. It's kind of the center of a cluster. In addition to the mean vector, in soft clustering, we also try to represent or model the extent or shape of the cluster. So we use this covariance matrix to encode the shape of a cluster. It might be very skewed into one direction or in another direction, and this can be encoded in a covariance matrix. So this is a mean vector. And we do the same for the other cluster. So we represent also cluster 2 by a probability distribution, by a particular probability distribution, which is a Gaussian with mean vector M2 and covariance matrix C2. Okay. So let's say, and again we have the circular problem. We need to start with having some initial choices for the means and the covariance matrices of a cluster, of the clustering. So a clustering is characterized by the mean vectors and by the covariance matrices. Once, let's say we have those given. So we have the mean vectors for both clusters and we have the covariance matrices for both clusters. How could we determine for a certain point, for a certain data point, let's say xi, the degree of belonging to cluster C1. So this is denoted by yi1, this quantity, the degree of belonging of data point xi to cluster C1. Any suggestions? How could we define this degree of belonging? If we model the whole data set using two distributions, two Gaussian distributions. Yes? The distance to the, so we could use the distance to the distribution. How would you define the distance to the distribution? Or the distance to the cluster mean? Yeah, so the suggestion amounts to kind of evaluating how well this data point, this particular data point fits into this Gaussian distribution of cluster 1. So how can we evaluate how well a data point fits into a probability distribution? Well, we just evaluate the probability distribution for this data point. You just evaluate the probability that this data point xi could have been drawn from a Gaussian with mean M1 and covariance C1. But then you also need to normalize in order to make sure that this is in the range 0 to 1 and it sums to 1. So we want these two degrees of belonging to sum to 1. So we have to normalize this by the sum of both components. So what is the degree of belonging to the other cluster? Which is the probability that xi could have been drawn from a Gaussian distribution with mean M2 and covariance C2. Okay. Yeah, and we do the same for the degree of belonging to the other cluster. However, since we enforce the sum of both to be 1, In the two-cluster case, we can directly read out the degree of belonging to the other cluster by 1 minus the degree of belonging to cluster 1. Yeah, so, and we do this for all data points. So we compute the degrees of belonging for all data points for the two clusters. How do we now move on? So we started with an initial guess for the cluster parameters. The cluster parameters here are mean vectors, covariance matrices. Based on the cluster parameters, we updated the degrees of belonging. What do we do now? Now we have found out the extent or the probability for each of the data points to belong to one of those two clusters. Well, what we can do, we can now update the model parameters like the mean vectors. Update cluster parameters, which are the mean vectors M1, M2, and the covariance matrix C1, C2. So we started with an initial guess of the Gaussian distributions. And then we evaluated how well do the data points fit these Gaussian distributions. This resulted in the degrees of belonging. And now with this measure, or with this information, we can refit the Gaussian distribution to the data points. So we can correct or update our beliefs about the cluster means, for example, by computing the weighted mean for cluster 1. So let's say we update cluster mean M1 by summing all feature vectors and weighting them with the degree of belonging to cluster 1. Then we divide by 1 over n. And we update the mean for cluster 2, similar. Xi times, how do we weight the data points for cluster 2? Sorry. Well, with the degree of belonging that the ith data point belongs to cluster 2. This is the degree of belonging of Xi belonging to cluster 2. Similar, this here is the degree of belonging, degree of Xi belonging to cluster 1. Well, actually, this is not the correct normalization because this 1 over n would apply only this. We have to normalize the means by the effective number of data points in cluster 1. So we have now effective sizes of the clusters, which is n1 and n2. And n1, the effective size of cluster 1, is just the sum of all degrees of belonging to cluster 1. And the effective size of cluster 2 is the sum of degrees of belonging to cluster 2. Okay. Let's put it here. And we can also update our estimates or guesses for the covariance matrix. I will not write out this. You can find these formulas in the book. So we can also update the guess for the covariance matrix of cluster 1 and covariance matrix of cluster 2, which are basically sample covariance matrices. This here is are sample means, weighted sample means, called sample means of the data points. And similar expressions lead to updates for the covariance matrix. So once we have found once we have updated the parameters of the clustering, how do we continue? So we have now reshaped the Gaussian distributions for the clusters. Once we have reshaped the Gaussians for the representing the clusters, what do we do? Yes? We recalculate the degrees of belonging, or cluster assignments, soft cluster assignments. Update soft cluster assignments. yi1 and yi2. Once we have updated the degrees of belonging, what do? We update the cluster parameters. Update M1, the shape of the Gaussian distributions which represent the clusters, C2, and so on and so forth. And this yields a soft clustering algorithm, which is based on a Gaussian mixture model. Yeah, you can find the details for this algorithm, as I mentioned, in the course book. And we will touch this we will ask you also to look at the implementation of the soft clustering method in a Python notebook for the next round, which will start on next Monday. Okay, so to wrap up, today we have considered two clustering methods. One hard clustering method called k-means, which associates each data point with one and exactly one cluster. And it does this by iteratively updating the cluster assignment given cluster means, and then updating the cluster means for a given cluster assignment. And we have learned one soft clustering method, which is based on Gaussian mixture models. The key idea of the soft clustering algorithm is to represent clusters using Gaussian distributions, which have a mean, which corresponds to a cluster mean, and a covariance matrix. So we also have now, in the soft clustering method, we use a finer control of the clusters. In k-means, we only used cluster means, whereas in the soft clustering algorithm, we use a cluster mean and a covariance matrix to somehow characterize the shape of a cluster. And we interpret this shape of a cluster using a probability distribution given by a multivariate normal distribution. The anatomy of the algorithm is pretty similar. Start with a guess of the clustering parameters. So the clustering parameters are here the cluster means and the cluster covariance matrices. Update the cluster assignments. The cluster assignments are given by the degrees of belonging for each data point. Given the updated cluster assignment, update the cluster parameters. Given the updated cluster parameters, update the cluster assignments. And continue this until there is no significant change in the cluster assignments, for example. You can come up with particular rules for when to stop the clustering, the soft clustering method, which is based on looking at the probability or the likelihood function of the Gaussian mixture model for the data set. So you can come up, similar to k-means, you can define a risk function or a cost function, and you can then look at how does this cost function change over iterations. So here we have, k is not a good symbol for iterations. Here we have iterations R. And over iterations, this risk decreases. So for each iteration, we get a new value for the cluster means, and we can use this cluster means to evaluate the risk function here. And the more iterations we use, the better estimates we get for the cluster means, and the smaller becomes this risk. And if you look at this, how this risk function evolves, you might stop if there is not a significant change anymore, or no change at all. So monitoring this risk function can be used to determine when to stop the iterations. Or another choice is you use a fixed number of iterations for k-means. But using a fixed number of iterations typically requires you that you know very well what happens, what k-means is doing. So you need to understand, you need to come up with a more detailed analysis of k-means. And those are available, but those analyses typically apply to particular data sets. In general, you might, what is kind of a generic approach to determine the stopping condition is to monitor the decrease in the empirical risk of k-means or of the soft clustering method. Yep.
Can you also use the way of determining the covariance method to, say, deal with probability in the hard clustering method?
Can you also use the...
So we calculate the covariance based on soft clustering, and we use the same method to calculate the probability of the clustering incorrect or clustering incorrect in hard clustering. Change hard clustering, final iteration, can you check the probability that belongs to?
Yes. So the question was, can you combine the result of k-means, so the clustering that is output by k-means, with the covariance or the Gaussian mixture model used for soft clustering? Yes. So you can evaluate the probability, or you can look at what is the probabilities of the cluster of the points in one cluster produced by k-means using the Gaussian model for the cluster in the soft clustering method. And if this is very small, then this might point at an inconsistency or an outlier. So you can detect outliers. That's one of the big advantages of probabilistic models. As soon as you specify a probabilistic model with a probability density function, then you can evaluate the probability density for a certain observed data point. And if this is 10 to the power of minus 10, this points at this might be an outlier. So probabilistic models provide an elegant means to detect outliers. Okay, any other questions? Okay, then have a nice weekend. And as I said, we will extend the deadline for quiz 3 till 5 minutes to midnight tonight.